Okay, this is the second part of 6C, and the problem says consider an exam taken by 1,000 students for which the scores are normally distributed with a mean of 75 and a standard deviation of 7. Okay, and so it's going to ask us some questions about here. So I'm going to go ahead and write down what we know, that we have a mean of 75, and it said a standard deviation. I'm just going to write standard deviation of 7. Go back up here. Yep. And so it says, suppose we want to know how many students scored above an 82. And it says, what does the 68, 95, 99.7 rule tell us? Well, what we know is that if things are one standard deviation away from the mean, either adding it or subtracting it, then that means that there's 68% of the population that are going to score in between that. So if we look at the 68%, okay, then we would need to look at the scores that were 75 plus 7, and we would need to look at the scores that were 75 minus 7. This would give us our new range. 75 plus 7 is going to be 82. 75 minus 7 is going to be 68. And so we've got 82 and 68. Got a range in between those two scores. And I'm seeing that in the problem it says, what percent scored above 82? Well, if 68% scored in between 68 and 82, then all of the rest, right, all of the rest, which would be 100%, so if we do 100 minus 68, scored outside of that, so that would be 32%. So when we're looking at this problem, we're talking about all of this that's on this side, and all of it that is on this side would make up this 32%. So we really are just interested in the people who scored above 82. So we need to, that would just be half of these, right? This would just be, this side makes up half of this. And so we need to do 32 divided by 2 to get 16%. So 16% of the population scored above 82%. This question says, suppose we want to know how many students scored below 61. Well, so far I found out an 82 and a 68. So that is not 61. So let's go out to the next standard deviation, which would be, let's look at the 95%, because it goes 68, right? It goes 68, 95, 99.7. So let's look at what's going to happen with that. You still start out with the mean, and you add 2 standard deviations, and then you also subtract 2 standard deviations to get those numbers. Okay, and 75 plus 7 times 2 is going to get you 89. And then 75 minus 7 times 2 is going to get you 61. And there's the score we're looking for, 61. So if we go back up here, this would get us the 61, and this is our 89. Okay, so in between 61 and 89%, that includes 95% of the population. So that means if we do 100 minus 95, that's going to give us 5%. Those people did not score between 61 and 89, and they're specifically looking for the people that score below 61. So the 5% that we're talking about that didn't score in between this is going to make up this part right here and this part right here. Okay, so we don't want this. We don't want this side. We only want the people that scored less than 61. So that would be taking our 5% and dividing it by 2, and that's going to be 2.5% scored less than 61%. Okay. Now, this says the 68, 95, 99.7 rule applies to data values that are exactly 1, 2, or 3 standard deviations from the mean. The number of standard deviations a data value lies above or below the mean is called the standard score, or the z-score, abbreviated by the letter z. Okay, a standard score for the mean is z is equal to 0, and that's because the mean is 0 standard deviations from the mean. The standard score of a data value with a 1.5 standard deviations above the mean would be a z-score is 1.5. A standard deviation, or a standard score for a data value that lies 2 standard deviations below the mean, would be z equals -2. So here's a formula for how to compute the z-score. You're going to take your data value minus your mean and then divide it by the standard deviation. And they're wanting us to do that for 85, 100, and 125. It says that we have a mean of 100 and we have a standard deviation of 15. So we're using this formula above right here. So if we're trying to calculate this for 85, okay, we would take our data value minus our mean of 100 divided by our standard deviation of 15. Okay, and that's going to give us -1. If we want to do this for 100, we're going to do 100 minus 100 over 15, which is going to give us 0. We're going to do this for 125, 125 minus 100 over 15, which is going to give us approximately 1.67, and you usually round these to 2 decimal places. Once we have the standard score for the data value, the properties of the normal distribution allow us to find its percentile in the distribution. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. A data value that lies between 2 percentiles is called the lower percentile. For example, suppose you scored in the 45th percentile on the SAT. This is interpreted as 45% of the SAT scores were lower than yours, or you scored better than 45% of those taking the SAT test. You can also say that 55% of the scores were higher than yours, or 55% of the test takers scored higher than you. So the standard score table on the next page allows us to determine these percentiles from the z-scores. So it says, example 6, find the z-score of 1.6 on the table, and then you'll see that 94.52 is the corresponding percentile. So I'm going to scroll down to the table to show you this. So we're looking through these values, and we're trying to find a z-score of 1.6. So I'm locating that right here, 1.6, and the percentile that goes with it is 94.52. Okay, what that means is 94.52%, or 94 52/100% of the data fall below a z-score of 1.6. Okay, 94.52% of the values have a z-score less than or equal to 1.6. And also a data value with a z-score of 1.6 lies in the 94th percentile. So it's given us a problem here. It says, cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a 20-year-old man with a cholesterol level of 190? Okay, well, we need to do the z-score. We've got the 20-year-old man, so he does fall in this group, and he has a cholesterol level of 190. So that's going to be our, when we're looking at our formula up here, that's going to be our data value. So remember, we need to do data value minus mean divided by standard deviation. So our data value is 190, and it says that we have a mean of 178. So data value minus mean divided by our standard deviation, and it tells us our standard deviation is 41. Okay. So 190 minus 178 is 12 divided by 41. It's going to give us, if I round, I'm going to round this, 0.29, which is 29. I mean, this is our z-score, sorry. Okay, so this is our z-score. So we need to go to our table and find out, okay, well, what does that mean? Well, let's go to our table and find out what 0.29 is. Now, we might not find the perfect value, so we'll have to round up. It looks like the closest one we've got a 0.25 here and then a 0.30. 0.30 would be the closest to 0.29. So 61.79 is what we would want to write down. Okay, so scroll back up here. So that's going to give us 61.79%. If we round to the nearest percent, that's going to be 62%. Okay, and what that means is basically 62% of the men between 18 and 24 are within this person's range that has a cholesterol value of 190. So that means that 62% of the population have a cholesterol value that is below 190, and about 100 minus 62 is 38, so about 38% have a cholesterol value that is higher than his at 190. Okay, part B. What cholesterol level corresponds to the 90th percentile, the level at which the treatment must be necessary? So we've got to go backwards this time. We've got to go and we've got to find a value of 90 on here. And it looks like the closest that we're going to get to the 90th percentile, if you look on this chart, is 1.3, 90.32. So that would be our z-score. So if we look at a percentile of 90%, the z-score that corresponds with that was 1.3. So remember, to find the z-score is equal to our value, which we don't know this time because we're looking for the value. It says what cholesterol level corresponds to that, so we're looking for it. Our mean is still 178, and our standard deviation is still 41. So we're trying to solve this problem. So the first thing we would do is use some algebra to get the x by itself. So we'll want to multiply by 41 on both sides of the equal sign to get rid of this 41 and get it to cancel out. So 41 times 1.3, that's going to give me 53.3 is equal to x minus 178. Then we would need to add 178 to both sides. That's getting me 231.3 equals x. So the answer to this is what cholesterol level corresponds to the 90th percentile, the level at which treatment may be necessary. So this would be the value, 231.3 would be our cholesterol level. Okay. So that is the end of Chapter 6, Part C.